To determine whether f is differentiable, we need to know the domain of the function and where it is smooth and continuous. So taking a look at a is a sine function. So this is for all real values. The sine function is defined for all real values. Same for cosine. Cosine is defined for all real values. It's smooth and continuous for the whole part of it. For tan, we have vertical asymptotes at 90 degrees, 270 degrees, etc. So when we have a vertical slope on the tan graph, then we're going to end up with, we're going to have non-differentiable points because those are asymptotes. So x cannot be equal to pi over 2 plus n pi. For cotan, it's the same thing. However, for cotan, those asymptotes happen at 90 degree shift intervals. So it's going to be at 0, pi, etc. So it's going to be n pi. For secant, it follows cosine. So wherever cosine is going to hit 0, that's going to be where we're going to end up with vertical asymptotes. So in the denominator, so x cannot equal, so this should have been x not equal to n pi. So for secant, it's going to be same as tan, x not equal to 90 degrees or pi over 2 plus n pi, and cosecant then follows the cotan. For 1 over 1 plus cos. Now, where the cosine is defined for all real values, so that embedded function has no restrictions. However, the denominator cannot be equal to 0. So this 1 plus cos in the denominator cannot be equal to 0. So that means that for g, 1 plus cos cannot equal 0. That means that cosine cannot be equal to -1. And on our circle, cosine is not equal to -1 at pi. And then it's going to be equal to that every 2 pi. So x cannot be equal to pi plus n2 pi. So I've graphed it down here. There's our function. So at pi, there's pi right there. We have vertical asymptote, and 2 pi over, we're going to get, or sorry, that's going to be 2 pi over, we're going to get another vertical asymptote, so it's not smooth and continuous at those points. Same thing could be said for sine and cosine, where they hit 90 to both hit 0, so where for h, where sine is equal to 0, so x cannot be equal to 0, pi, etc. So we're going to say n pi. And then for cosine, cannot be equal to 0 either. So x cannot equal pi over 2 plus n pi. Okay? And when we look at the graph, we can see that that happens at pi over 2. Okay? It happens, we have one at pi, we have one at 3 pi over 2. That's a 3 there. And we can define it that way. We could also use an identity here, and this can be equal to 2 over 2 sine x cos x. Well, 2 sine x cos x is an identity. It is sine 2x. Okay, so it's going to happen where sine 2x is equal to 0. Well, sine 2x is equal to 0 at 0, pi over 2, pi, 3 pi over 2. So we're going to have these come together as x is not equal to, it's going to be sine of 0 at n pi over 2. So every 90 degrees. And lastly, for f, we don't worry about the cosine in the numerator. That's okay. It's the denominator that we have to be concerned about. So where for I, for 2 minus sine x is not equal to 0, well, this means that sine x has to be equal to 2, and sine x is never equal to 2 because the range of sine is just between -1 and 0. So this is going to be, x is going to be defined for all real numbers. And we can see that by looking at the graph of that function in green here, yeah, that's going to be all real numbers. There's no gaps. It's smooth and continuous throughout.